Okay, so the topic for today is solving LPs. So we've had multiple discussions about LPs, and I had said that there are many algorithms to solve linear programs, and today let's talk about two very important algorithms: the Simplex algorithm, and we'll talk about the Ellipsoid algorithm. So the Simplex algorithm was given by Danzig in 47. It is a classic and very important algorithm in computer science and mathematics. Its worst case time is exponential. So the worst case is exponential. But it's actually very efficient in practice. And there is some theory known for why. I mean, there are some theoretical explanations of this. This is Spielman and Teng, I believe, in 2001. They introduced something called the smooth complexity analysis, or they defined smooth complexity analysis, and they showed that the Simplex algorithm is polynomial time under some smoothing, so under some natural conditions on the input. But let me tell you how the Simplex algorithm works. It's also a good way of getting more understanding of the dual. So let's just start with a general LP, and we phrase it as a maximization problem. So let's say we're doing max C transpose X, AX less than equal to B, and X prime greater than 0, where this is some subset of variables. I'm going to convert the general LP into a more convenient form, and then I will run the Simplex algorithm on that more convenient form, and that will simplify a lot of our discussions. So firstly, there is some subset of the variables that is non-negative. I would like to make all the variables non-negative. So here is what I do. I replace any unconstrained x, let me just call it xi, by xi upper minus xi lower, where xil and xiu are greater than 0. So I can replace any unconstrained variable by the difference of two non-negative variables. And if I do that replacement here, I can essentially make that condition just x prime be greater than 0. So all the variables are non-negative. So these are sort of common transformations that one does to an LP so that it's easier to argue and easier to solve. It doesn't really change the underlying solution in any way, but then the math becomes easier to describe. So secondly, what I would like to do is actually convert all of the inequalities into equalities, so that the only inequalities that remain are the non-negative constraints. So the way that is done is by introducing slack variables. So let's introduce slack variables. So how does a slack variable work? So remember that I'm just drawing out the LP here. So this is A, X less than equal to B. And recall that I can look at any row and I can call the row AI star. Right? AI star is this row. So what you do is, if constraint is AI star X less than equal to BI, then replace with ai star x plus a slack variable that I will refer to as yi equal to bi and make yi non-negative. Actually, I should be doing this the other way around, so you subtract, I'm sorry. Right, so this condition, this pair of constraints here is equivalent to the constraint above. Wait, am I doing this? I'm sorry, my apologies. No, it should be a plus, I'm sorry. Right, so it's ai plus, right, of course. So I can replace this constraint, which is an inequality, by an equality constraint and a non-negativity constraint. And if I do this, and let me just relabel the x, y's, and let me just call them x's, just so that we can keep our notation low. I get what is called the slack form, which would be maximizing C transpose x, ax is equal to b, x is greater than 0. So any LP can be written in slack form. While the slack form would not be convenient when we want to argue about the LP mathematically, because all these extra constraints can sometimes can cloud our understanding of the LP. From a computational standpoint, when we replace by a slack form, then describing an algorithm that solves the LP becomes much easier. So I'm going to make a few assumptions here. So let me just get some notation straight. So this is my matrix A, and I will refer to this, it'll be an M cross N matrix. It's an M cross N matrix. So you can think that so firstly what we can do is we can ensure that the rows are linearly independent. Now, if not, then some equality constraint is a linear combination of existing constraints so either we can remove it or determine that the LP is infeasible. Right, because if any one constraint here, so I should write, this is our constraint. If any constraint over here, if any row is a linear combination of other rows, then the corresponding B should also be the same linear combination. And if it is the same linear combination, you can just remove that row. And if it is not the same linear combination, then you know that the LP is infeasible because all of these constraints cannot be simultaneously satisfied, like even ignoring the non-negativity constraint. So we can ensure that the rows are linearly independent. Okay. So I'll just keep this picture in front of us. Keep this view. And so we also know that we'll assume that M is less than N, because if not, then the solution to AX equal to B is unique. We can find the solution the solution X and check that it's non-negative. So we can assume that m is less than n and all the rows are linearly independent. And so this is exactly the picture that we have here. I'll just draw this again. Right, so this is A, M, N, A, X, and B. I'm just going to draw C over here, right? Because we want to maximize C transpose X. So C is also n-dimensional. Okay. Now, given the primal, it is natural that we write the dual. So let me write the dual here. So what am I going to have in the dual variable? I have a dual variable for every y, for every constraint. Right? So the variables here, the variables, and so of course I have x greater than 0, are x1 up to xn, and the variables over here are y1 to ym. Now, note that these are equality constraints, so the yi's are going to be unconstrained. We are going to minimize y transpose b. Right, we're going to minimize y transpose b. And because this is a maximization problem, we are looking for an upper bound on the objective. And so we're going to multiply, you can think of it as we're going to multiply each of these constraints by yi, take the sum, and you want, whatever that sum is going to be, we want that to be greater. We want that to be greater than the c's. And because x's are unconstrained, x's are non-negative, basically when you take the dual, you will get y transpose A is greater than C. Right? And because this is a non-negative random variables, you have a greater than equal to here. And because these are unconstrained, these are equality constraints, right? So the constraints correspond to the, when you have equality constraints, you have unconstrained variables. When you have non-negativity constraints on the variables, you have inequality constraints. So this is the dual. Right? So the dual is given over here. Right, any questions? All right. And before digging into all of this, let me just write down, as usual, we have a primal, we write down the dual, we write complementary slackness. Now, complementary slackness, these constraints are all equality, so there's really nothing much to say over there. But here you have inequality constraints. So we know that for any constraint, either it's an equality or the corresponding dual variable. In this case, the corresponding primal variable is going to be 0. So I'll write this out as saying that if x star I is equal to 0, so this is the optimal. This is some optimal solution, is not equal to 0, then the corresponding constraint, which would be y, well, let me not put a star here. Let me just say if, I'll put a hat for optimal. So if x hat I is equal to 0, then y hat transpose of A star I is equal to Ci, which means that you're looking at if x star I, so if a corresponding variable here is non-zero, then you're looking at that column, that A star I is the column. Right? Because what we have, another way to look at this is we have a dual variable for every row of the matrix and a constraint for every column of the matrix. Okay, so this is complementary slackness. Okay, so any questions at this point? All right. Now we come to a very important concept of what is called a basic feasible solution, sometimes written as a BFS, not breadth first search, but basic feasible solution. So going back and looking at our matrix, so this is an equality, right? AX is equal to B. So we are going to construct a basic feasible solution as follows. Take our matrix. Let B be a subset of columns. So B is a subset of columns. And indexing the columns going from 1 to n, I'll just say that B is a subset of n of size m, right? So this is going to be, remember, this is m. So I'm picking m columns here, such that these columns are linear independent. In other words, the columns form a basis. And it's a basis of R to the m. So given this, we will say that A sub B is the square submatrix. Right? So this is a square submatrix of these columns. So B is a subset of m columns, which are all linearly independent, so they form a basis. So AB is a square submatrix of full rank. And so a basic feasible solution has the following properties. So let me define a basic feasible solution, also called a BFS, is sort of, I'll say, as a primal point x sub b. I should say a basic feasible solution maybe for B, such that AB of xb let me write this out. Okay, so is a primal point A such that AB of xb is equal to B, and for all I not in B, xi is equal to 0. So what is this saying? This is saying you want to solve AX is equal to B. I'm just going to take a basis. So that basis will correspond to exactly m entries in X. I will set all the other entries to be 0 and simply solve for these entries. And that gives me XB. Right? So I simply solve this. This is a much simpler system. This is just a full rank system. So I solve AB XB equal to B. I set everything else to be non-zero. So it satisfies these conditions, and for all I, xi is greater than 0. So a basic feasible solution is essentially a point that satisfies the LP, right? Because AX is equal to B, because you set everything to be non-zero, everything else outside B to be 0. The only possible non-zero coordinates correspond to the basis, and all the xi's are greater than 0. Any questions about a basic feasible solution? Geometrically, what is this indexing? Geometrically, what is going on? Anyone have any intuitions or thoughts?
I'm actually kind of unsure about AB. Can you explain what exactly AB does? Like, is it any submatrix of?
So, by the way, so there is a question in the chat. No, it's actually not C transpose, because if you think of y as a column vector, so let me just sort of write this out over here. So here is A, and you think of y transpose as a row vector because it's y transpose. So when you take the matrix product, you will get another row vector here. So C is a row vector. Hopefully that answers that question. Sorry, so what was the comment before? I missed that.
I'm slightly unsure about AB. Could you repeat what like the definition of AB once more?
So yeah, okay. So I'm defining a basic feasible solution as follows. So I'm going to take a subset of columns I'm going to take m columns which are all linearly independent. So if I look at the matrix given by those columns, this is the matrix restricted to those columns. So this is the restriction to B. Restriction of A to the columns B. Does that make sense now? So then that gives you a square submatrix.
So this, if there's actually more than one possible option for m linearly independent columns, then that's also fine.
Yeah. So this is just saying this is just saying that this is a basic feasible solution. There exist many.
Okay, yeah, that was my question.
There exists many.
Yeah.
But what is this geometrically?
So this is this is an intersection of faces of the feasible solution of the feasible region if it's closed.
This is essentially, yes, this is these are going to correspond to vertices of the polytope. And I'm going to show you.
Not just edges?
Sorry?
It's not just edges, it's actually a vertex.
You are going to get vertices. You're going to get vertices. So the way to think about it is, okay, so this is your solution is sitting in R to the M. I'm sorry, R to the N, my apologies, R to the N. Your solution is sitting in R to the N. And you have these M hyperplanes. And you're looking at the intersection of those hyperplanes and then closing it off with non-negativity constraints. So that gives you your polytope.
So when we are actually doing, so that's my intuition as well, but when we are looking at intersection of the faces, should we also be getting edges, not just vertices?
You will get, facets of all dimensions, right? Vertices, edges, so on and so forth. You will get facets. You're right that these points are going to be basically like, on the facets. But yes, so the point is that these are the points that are going to be lying on the boundary of the polytope. These are the points that are going to lie at the boundary of the polytope. Let me actually now make some of this more clear as to why should I be looking at points of this form. Okay, so I'm going to give you another definition. So technically this is not a definition, this is actually you can call this actually a claim, but I will state it as a definition. I will say a feasible point V is a vertex of the polytope. So I'm assuming it's it's all bounded and well, okay, or maybe I should say polyhedron. If and only, so this is this you can think of as a definition, or you can think of defining vertex as basically a face of dimension 0 and then trying to prove this claim. So it depends on how you want to look at it, but let me write this sort of as a definition. If there does not exist a W, and so remember this is a point in Rm, such that I'm sorry, Rm, such that there does not exist a W in Rn and an epsilon greater than 0, such that both V plus epsilon W and V minus epsilon W are in the polytope. Right, so what is it saying? It says here's my V. If I can put a line through V such that both of these points are in the polytope, then V is not a vertex. So V is a vertex if and only if for all lines, whenever I put a line, so if I take a vertex, if I put a line through this, so either like no point lies in here, or at most one side lies in here. So this is essentially an equivalent definition of a vertex. And I'll just draw maybe a 3D figure over here just to show you that if you have a point on this, you could look at this line and therefore it would fail the definition. Therefore points along this line are also not vertices. It's only the corners that are going to be vertices. This is me. So a feasible point is a vertex of the polyhedron, essentially if and only if there does not exist any W, so that both V plus epsilon W and V minus epsilon W are in the polytope. Okay, is this clear? Any questions about this definition? Definition, claim? Okay. Now let me prove a convenient claim to you which will explain why I care about basic feasible solutions. So the claim is that any vertex of the LP or the polyhedron has at most m non-zero coordinates. Okay, so this is some useful linear algebra to do, so let's prove this. So I'll just say suppose V is a vertex and has strictly greater than m non-zero coordinates. And V is greater than 0, right? Because V is a vertex of the polyhedron. So let's say it's a vertex of the polyhedron. It has more than m non-zero coordinates, and V is greater than 0. So let me write this as follows. So I think it's useful to draw the picture here. So what I claim is, because there are m non-zero coordinates, let me look at the corresponding columns in those coordinates. So these are the columns of those coordinates of the m greater than m non-zero coordinates. Rearranging the columns Um, so I'm just going to rearrange the columns or the coordinates so that v1, v2 up to vm plus 1 are strictly positive. So I'm just going to rearrange the columns so that there are m plus 1 columns here, and if I look at my v, all of this portion is strictly positive. All of that portion is strictly positive. And the whole point is this, on the other hand, is m, and you have m plus 1. So note that a star 1, a star 2 up to a star m plus 1 are linearly dependent. They are linearly dependent because you have m plus 1 columns or m plus 1 vectors in m dimensional space, so obviously they're linearly dependent. And again, by rearranging among them to get a basis, so I'm sort of fudging the subscripts here, but I can assume that a star m plus 1 is a linear combination of a star I going from 1 up to m. I'm saying the last column is a linear combination of the first m columns. I can always rearrange the columns to ensure this happens, right? Because I know there's a linear dependence. And if there's a linear dependence, then I can just take one of them that's linear dependent and move it to the end and keep all the other columns. This is just going to keep the indexing somewhat convenient. Okay? Alright? Okay, now here is the key. What I want to argue, what I need to argue, I want to prove that V is not a vertex. I need to find a W and an epsilon such that both V plus epsilon W and V minus epsilon W are in the polytope. That means I need to show that V plus epsilon W and V minus epsilon W are both feasible. So they need to satisfy the linear conditions and they all have to be non-negative. So I need to find these vectors. I need to find this vector W and this parameter epsilon. So I'm trying to find out how do I perturb V to show that it is not a vertex. And I'm getting it simply because of the fact there are m plus 1 non-zero coordinates. Alright? So I know that A times V is equal to B. Right? Because V is a vertex of the polytope, it is feasible. And V is greater than or equal to 0. So what is A times V? I can write this as a linear combination of column vectors. So here is B. So that's just saying that the summation of I going from 1 to, okay, so let me do actually 1 all the way to n of A star I times Vi is equal to B. Right? This is the same thing as this. These are equivalent. Okay, now just take the summation of this going to m plus 1, just the first m plus 1 parts here. Okay, I'm just going to rewrite this as the summation of I going from 1 to m of A star I Vi plus A star m plus 1 V m plus 1. Right, just looking at the first m columns and then the last one. So I know that this is a linear combination. So let me just plug that in. So A star I Vi plus the summation of I going from 1 to m of alpha I A star I Vm plus 1. Now using these, I'm going to actually compute my W. So the way that I'm going to do this, sorry, so let me explain. Okay, so now I need to find, what I'm going to do is I'm going to show that I'm going to perturb Vi in such a way that this sum is not going to change. And if the sum doesn't change, then this constraint does not change. And therefore, it remains to be feasible. So let me define Wi to be alpha I for I less than m, and Wi plus 1 to be minus 1. And everything else is 0. All others are 0. All other coordinates are 0. Okay, so here is my V. This is V. When I look at the first m plus 1, and these are non-zero, I don't know what's going on here. So here's going to be my W, where I set these to be alpha 1 up to alpha m. I set this to be minus 1, because this is exactly the linear combination that I get from here. And choose epsilon sufficiently small so that Vi plus plus minus epsilon alpha I is non-negative. Right, so I can choose that because all of these are strictly greater than 0. So I multiply this by something, so epsilon and V m plus 1 plus minus epsilon is non-negative. So I'm just saying that I choose epsilon to be sufficiently small so that when I add epsilon times alpha I, or just minus epsilon to Vi, then it will remain non-negative. So observe that V plus epsilon W and V minus epsilon W are non-negative. Furthermore, here's what's important. I think this was written poorly by me. A times W is equal to 0. I'm sorry, I probably should not have. That was a little confusing. A times W is equal to 0 because of this, right? Because A times W is exactly summation of I from 1 to m alpha I A star I minus A star m plus 1, which is equal to 0 by the linear dependence. So A times W is equal to 0. Hence, A times V plus epsilon W is equal to A times V is equal to A times V minus epsilon W, right? And all of this is equal to B. So both V plus epsilon W and V minus epsilon W are feasible. And there's your contradiction. Right? So basically it says that if you have strictly more than m non-zero coordinates, then basically by some linear algebra, you can do some column rearrangement, you can move things around, and what you can deduce is that actually V is not a vertex. Consequently, any vertex has at most m non-zero coordinates. And that then connects to our basic feasible solution, where we basically select m non-zero coordinates. So here we select m non-zero coordinates. right? Because that's exactly given by the basis. Any questions at this point? I can pause here and take any questions that you have to make sure that you understand what's going on. Because once you understand this, the simplex algorithm becomes fairly easy to explain. Yes? Questions? Okay. So again, if you missed the calculation, that's okay, but any vertex of the LP has at most m non-zero coordinates. So good. So now that we have that, we also know that the optimum, if it exists, is a vertex. So any vertex is defined by a subset B of m columns, and that's what we need to find. We need to find which subset is going to be the best choice, and note that there are n choose m different possible choices for B. And now here's the idea of the simplex algorithm. It says we need to assume that we can start from some feasible basis, but let's just assume that. So suppose we have a BFS X corresponding to B. Right? So what does that mean? It means AB XB is equal to B. What we'll do is we'll solve the dual. We'll solve the dual of Y transpose AB is equal to CB transpose. Note that AB is a submatrix of full rank. AB is a submatrix. A sub B is this submatrix of full rank. So what we're saying is, one way to look at this is, we decided that we picked a few columns here. We solved that to get B. We're going to pick the same columns here. We're going to pick the same columns here. And we're going to solve an equality with C. So we're just going to say that Y transpose of those columns is equal to C. Let's just go ahead and solve it. Because it's full rank, we can solve it. Now what is important over here is to observe that X and Y satisfy complementary slackness. Why? The only X's or Xi's that are non-zero are for I is equal to B. I is in B. Right? Because by the basic feasible solution, so let me just draw this picture again. Let's say we selected these M coordinates, and I'm just going to put them at the beginning. I'm just going to make B in the beginning. So this is XB. Everything else we just set to 0. So this is the only portion that is non-negative. It's the only portion that is non-negative. But these are exactly the constraints in the dual that we set to equality. Right, so if you put C over here, we solved for Y such that this is an equality. That's what we solved here. So this is getting complementary slackness. for free. Or rather, this is essentially enforcing complementary slackness. So it's like a primal dual approach here. This is a very important point. Does this make sense? So please ask me any questions. Is this clear why this satisfies complementary slackness? Because I basically cooked up my y. My y transpose b is just saying y times each of these columns should be equal to the c, the cb that's over here. Questions, please. This is a very important point. So if something is unclear here, please ask me to explain. So x and y satisfy complementary slackness. X is feasible. So if y is feasible, then we're done. We have the optimum. Because if you have x and y being feasible and satisfy complementary slackness, you're done. So, if y is not feasible, what does that mean? Remember, y transpose A has to be greater than or equal to C. So if y is not feasible, then one of these constraints is failing. Okay? So one of these constraints is failing. So we need this to be greater than or equal to C. And so one of these constraints is failing. So maybe this constraint fails. Right? So essentially the constraints of the dual correspond. Sorry, just a second. Yeah. The constraints of the dual correspond to columns. So if y is not feasible, there is a column, there exists some, I'll refer to this as j in n. So some column j such that y transpose A star j, that constraint is strictly less than Cj. So in some sense you have found a coordinate in the objective which is really large, which means that we would like to increase x on this coordinate. Right now x on that coordinate is 0. So what we're going to do is we want to increase the value of x on that coordinate and correspondingly decrease the value of x on the remaining coordinates, so that we can maintain feasibility. Okay? So what we'll do is, if y is not feasible, there exists this j. We want to introduce or maybe insert j in B and remove something in B. And this is referred to as a pivot. When you pivot, you basically bring j in and you take someone out. Now I want to explain how the pivoting operation does and why the math works out. So here's how we pivot. We want to introduce j in, but we need to now change the values we need to change the values of xb, right? What we want to do is here's some xj. And we want to increase xj. But to increase xj, we need to decrease the xb's, because eventually, this thing has to be equal to b. Right? A times b, or the a times x has to be equal to b. So when we increase this, we're going to decrease some of these to compensate. And how do we find out how to compensate? This is exactly how the previous proof goes. So let's actually solve a b of z equal to a star of j. What does this mean? Because the columns of B are a basis, I can write a star j as a linear combination of the bases. So this is just saying that a star j is going to be equal to the summation of a star I, where I is in B, of z I. Right? This is just saying that I want to write A star j as a linear combination of these columns. That's exactly what this is saying. Like, ignore the fact that you're solving a linear system. Just think of it as you're trying to find A star j as a linear combination of the columns over here. Okay? Now let us set x b. Let's reset this with xb minus epsilon z. Remember, z is just some linear combination. Z corresponds to, z is a vector of dimension exactly m, right? Because they're b, it has size exactly b. So I can subtract out that, and I'll set xj to be epsilon. So let me just go ahead and make this change. This is not the pivoting. This is just telling you that when I make this change, you'll see that the objective value is actually going to increase. So what is the new value of the objective? The new value of the objective is CB transpose XB minus epsilon z plus Cj times epsilon. So CB is like this, saying that here's C and CB is just this portion here. Here is X, here is XB, and here is XJ. So I increased XJ, right? So that I made that epsilon. So that gives me the Cj times epsilon. And I decreased XB, so I'm just plugging that in over here. So the new value of the objective here is CB transpose XB. Plus epsilon Cj minus CB transpose of z. Right, so this is exactly what I get over here. Now I'm going to rewrite this. So this was the old objective, right? So this is CB transpose XB plus epsilon Cj minus, now what is CB transpose? That is Y transpose AB, because I solved that to be an equality. So CB, sorry, is that a transpose? Yeah, that's fine. CB transpose is that. Okay, good. Because CB is, right. So CB transpose is exactly Y transpose AB Z. But then AB of Z is basically A star J. So what I get here is CB transpose XB plus epsilon CJ minus Y transpose AB is what I put in, but AB times Z is A star J. So I get this minus Y transpose A star J. But this is strictly less than Cj. That's why I chose J. And so what I get here is this is strictly greater than, or this is greater than equal to CB XB for all non-negative epsilon. So for all non-negative epsilon, this holds. Okay? So does this make sense? This is essentially, this is the pivoting rule. This is, well, we'll see the pivoting rule shortly, but this is how the simplex algorithm works. You start with a basic feasible solution. AB XB is equal to B, right? So you have B, AB times XB is equal to B. What you now do is you say, well, let me solve Y transpose AB is equal to CB transpose. I mean, technically this is CB transpose, right? So I'm going to find out Y such that when I multiply with each of these, I take a dot product with each of these, I get CB. So I get Y transpose AB. So if They satisfy complementary slackness. If y is feasible, I'm done. If y is not feasible, then I find some constraint that's violated. So y transpose A star j is strictly less than Cj. At this point, I will demonstrate how you can potentially increase the objective value by setting xj to be epsilon and reducing xb by z, where z is like the linear combination of the basis that gives you j. And so once you put all of these things together, you get this. So the question is, what should you set epsilon to be? I haven't told you how to set epsilon. I just set this. I said, okay, let's just make it some epsilon. But you need to ensure that epsilon is set in such a way that these are feasible. And so at this point, we end up with three situations. So three situations. Well, before I get to those three situations, let me first explain something.
It's a little out of focus. Okay.
Yeah, I focused it. To ensure that the new x is non-negative, we choose epsilon such that xb minus epsilon z is non-negative, right? This is what we need. I should say that, you can show, just as in the previous proof, you can show that for the new x, ax is equal to b. This is exactly like the calculation of the previous proof, and that's why you chose this in such a way. So you just ensure that the xb minus epsilon z is non-negative, which means you choose epsilon equal to the min of the basis of xk divided by zk. Right? You just choose this, and if you ensure this, then all of these will be non-negative. Now here are three situations. Situation one is that we can choose epsilon to be arbitrarily large. If we can choose it to be arbitrarily large, and that would happen essentially if the zk's turned out to be, if you had zeros in the zk's, then you could set it to be arbitrarily large, maintaining you have to choose, I should say that you have to choose this to be non-negative. Now suppose suppose some of the zk's were actually negative. Some of the zk's were actually negative. Well, in that case, you could make epsilon be arbitrarily large. So arbitrarily large, maintaining xp minus epsilon z is greater than 0. So suppose you can choose epsilon to be arbitrarily large. Then what does that mean? What does that mean? Any comments? So suppose I could set epsilon to be arbitrarily large, then what would happen over here?
X naught is unbounded.
Sorry, say that again?
X naught unbounded.
X naught, you mean the objective, the value of the objective?
Yeah.
Is unbounded, exactly, which means the LP is unbounded. In this case, that means the LP optimum is unbounded. Or you can think of
So
it as it doesn't
that's
exist.
xb. Sorry.
I'm sorry?
That's xb from the same xb as above. Okay.
Yeah. Yeah. But the LP then is unbounded, right? Because what this means is you can keep increasing epsilon and you would keep increasing your objective value here. But we said that and you would maintain non-negativity. And you can show that for any choice, for any new x, ax is equal to b. So you can keep increasing epsilon and then it becomes unbounded. So you just terminated this case, right? So just terminate because you know that there is no optimum. The second case, which is there exists some maximum choice of epsilon. So I should say this is only for the non-negative. So there exists a maximal choice of the maximum positive choice. A strictly positive choice such that xb minus epsilon z is greater than 0. For this choice, for some I in B, you'll get that xi minus epsilon zi is going to be equal to 0. Because if not, then you could increase epsilon even more. So what this means is then you can update the B to be B union J, which is what you wanted to do, removing I. So this is the pivot, and the objective decreases. Objective decreases. And the third choice is that the only possible choice is epsilon being 0, which could happen. You can still update. So you know that there's going to be something for which it's 0. So you still update by B union J minus I. But the objective stays the same. Now when this is 0, in case 3, we basically replace a 0 in xb by a 0 xj. Because if the epsilon is 0, then this is 0. Now in this case, because the objective stays the same, we can potentially cycle through bases, and the simplex won't terminate. And the simplex algorithm does not terminate. So there are simple fixes. We use typically we use like a lexicographic tie-breaking rule. To ensure termination. So you can basically, in some sense, order the coordinates in such a way that you'll never do the same, you'll never come back. And this is often called a pivot rule. And this switching over here, this is called pivoting. And so this is basically the simplex algorithm. I'm just going to write out quickly a description of the simplex algorithm, just so that you have it. So the simplex algorithm. So you start with some BFS x b. And in general, if you don't, there is a process of finding such a basic feasible solution using the simplex algorithm, and I'm going to make that an exercise. So the procedure basically just says while true, solve y transpose A is equal to CB if y transpose A, if the entire thing is now A, B is equal to CB, then we're done. You have the optimal solution. There exists a J such that y transpose A star J is less than Cj. So we're going to solve ABZ equal to A star J. Then we determine largest epsilon, non-negative epsilon, such that for all things in the basis, xk minus epsilon zk is greater than 0. And now what we say is, I'll just put it over here, if epsilon is unbounded, then terminate. Otherwise, there exists an I such that xi, an I in the basis, such that xi minus epsilon zi is equal to 0. Then you reset, B is equal to B union J minus I, and update x. And this is the simplex algorithm, and the key is that you use complementary slackness in step 1, and then there are these linear algebraic calculations for what remains. So this is the simplex algorithm. We have about 20 minutes left, so I'm going to pause here for a couple minutes, and then I'll give a high-level description of the ellipsoid algorithm. Okay, so let me now tell you about the ellipsoid algorithm. So this is by Kachian, I believe 72. It is a weakly polynomial time algorithm for solving LPs. And the weakly polynomial time, one way to think of it is to get solution with k bits of precision, we need polynomial in k overhead. So one way to think of it is it's going to give you more and more precision as you run it more and more. And of course, at some point, if you have some bound on how much precision you need for your output, then you can, it will terminate. Okay, the first step is we reduce finding optimality to checking feasibility. So we're going to do this reduction, and if you think about it, it's basically just binary search. It's just binary search, because to solve max C transpose X, Ax less than B, we basically solve it to something like, so suppose given a range that C transpose X we know is going to be in, let's say, alpha and beta. And often for many problems you can come up with some kind of range just by looking at the maximum coordinates. Or if you know that you're solving, let's say, a matching problem or something, then you can easily come up with a range for this setting. And so to solve this with this given range, instead we'll solve C transpose X being less than, I'm sorry, we're trying to maximize. So C transpose X being greater than alpha plus beta divided by 2, AX less than B. Right? And this is just a set of linear constraints. So just check feasibility here. And so if feasible, then range is alpha plus beta by 2 beta, and if not, then the range is alpha plus beta by 2. So you can do binary search and see that binary search is sort of related to the precision. So you pay the log of your range, and the log of your range is the precision. So essentially you can reduce finding optimality to checking feasibility. And so let's just think about checking feasibility. So we need to check feasibility of AX less than equal to B. So here's the main idea. So this is some polytope. Polytope, polyhedron, let's just say it's a polytope. Suppose we have a bounding, let's just say a bounding sphere containing P. And technically this is going to be an ellipsoid. So what we have is you have your region here, your polytope here, and you have some bounding sphere. Right? So you have some bound. In general, what we'll have is, instead of a bounding sphere, we'll have some sort of bounding ellipsoid. So what is an ellipsoid? An ellipsoid essentially is given by the equation summation xi square divided by ai square is less than 1. That's an ellipsoid. So if all the alphas are the same, this is a sphere. So one way to think of it is it's like a sphere, except you stretch out certain dimensions. So this is an ellipsoid. This is an axis parallel ellipsoid. So what's important to note is that, this is, you could do rotations and you would get a different equation, but essentially after you can almost rotate so that an ellipsoid looks like that. So let's just say we have a bounding ellipsoid that already contains the polytope. And let's say initially you can find this by just taking a bounding sphere, like take a really large sphere that contains your polytope. Now here is sort of the key operation is, let's just translate coordinates so that the origin is the center of the ellipsoid. Right? So we can just move our axes so that something like this. Although note that in general you could have some ellipsoid of that form, and maybe your convex body lies in here. You just have a bounding ellipsoid. You don't really know where the body lies, and you just want to check feasibility. Find a point or reject. So what we do is we do some kind of sophisticated version of binary search. We just check if the origin is feasible by just plugging into the LP, right? You could plug it into the LP and check. If it's feasible, then you're done. So in these cases, you'd be done. But in this case, you would plug that in and you would say, well, it's not feasible. Now here is the key, is you find a hyperplane passing through the origin. It's not even important, or I would say find a hyperplane separating the origin from P. So you find what's called a separating hyperplane. So it says if you're in the situation, just find some hyperplane such that the origin is on one side and the body is on the other side. So just get some hyperplane like that. Now how would you find such a hyperplane? This could just be, this is given by a constraint that is violated. So if you have a constraint that is violated, then that would be a separating hyperplane. So in this case, that could be a separating hyperplane, or even this could be a separating hyperplane. You have multiple separating hyperplanes. This is not a separating hyperplane because the body and the point, the polytope and the point lie on the same side. So you find a separating hyperplane. So this determines that P is contained in a half ellipsoid. Right, so what is a half ellipsoid? So here's your ellipsoid that you started off with. We don't know where the point is. We found some separating hyperplane. So we know that the body lies somewhere in here. Now what we do is we find a smaller ellipsoid containing the shaded region. And this is the magic. So what we do is we need to find some sort of ellipsoid like that. You find the ellipsoid of that form, and then you have to argue that it is actually smaller. And this is, you can find some what's called the minimum enclosing ellipsoid. So you find a smaller ellipsoid that contains this region. And the insight is that it is possible to find the smaller ellipsoid with some algebraic calculations. And I can even show you what those algebraic calculations are. They're not that hard once you see them, but it's sort of, the insight is remarkable. And what you get is that the volume of the ellipsoid shrinks by a fairly small amount, shrinks by 1 minus 1 over n, where n is the dimension. So you can argue that this ellipsoid is going to be a little bit smaller, just by 1 minus 1 over n. But the volume has shrunk. And then you just repeat this procedure over and over again. I mean, whatever you do, it's like binary search at some level, right? Then again, you would look at the center of this point, you would query that, and if that is actually not in the in P, the polytope, then you find some separating hyperplane, and then you get a minimum enclosing ellipsoid of whatever is left. You can just ignore the older ellipsoid. So if you let EK be the ellipsoid at the kth iteration, Then there's a theorem that you can show. You can show that the volume of ek plus 1 is at most 1 minus, I think it's like technically 1 over 4n of the volume of the previous ellipsoid. So the ellipsoid is going to shrink.
I have a question.
Yes.
So this ellipsoid, like the best we can do then is recursively is going to be 1 by e of the total initial ellipsoid volume that we started with, right?
1 by e? What do you mean by 1 by e? I mean, you do it n times and the volume will shrink by a 1 over e factor.
Yeah. So how is that sufficient to reach a solution?
Yeah, okay. So but good question. So let me write something here that is going to clarify that. So I'll say after k is equal to n times r iterations, or maybe I'll say something like 4 nr iterations, the volume of the ellipsoid is at most 1 minus 1 over 4n to the power 4nr, and this is basically like e to the minus r, right? So what this means is, if we have a lower bound on the volume of P, let's say a lower bound on the volume of P, then we know that K only needs to be something like O of n log of P iterations. So if you have a lower bound on the polytope, then you'll find it, because after these many iterations, the enclosing ellipsoid would be smaller than the volume, which is absurd. Does that make sense?
Yeah, like I understand this theorem. I'm still not sure how I get a solution on this problem.
Well, okay, if you have a lower bound on the volume, then do you agree?
Yeah.
So you need a lower bound on the volume.
Yeah.
Now that, let me show you. So if you, so you need n log of the volume of P. So what you can do is, if you consider the polytope ax less than b, such that the feasible region is full dimensional. You know, for now, ignore the fact that the feasible region might be empty. Let's just say the feasible region is full dimensional, suppose. Right? So it's basically some full dimensional polytope given by ax less than b. Then, so I'll say the polytope is P given by, then we can prove that the volume of P, so you can prove that it's at least, okay, so I'm going to write something here and then I'll explain it. I'll say the volume is at least A max times B max to the minus, you get something like minus some polynomial in n. And these are just the largest values in A and B. So you can prove that the volume of the polytope is going to be at least the largest values to some power value. This is tiny, but the number of iterations that we need is O of n log of the volume of P. And so this is basically going to give you O of poly n times the log of A max times B max. And so this is the weakly polynomial part. This, it ends up being some amount of linear algebra, right? Because essentially, if you look at any of the vertices of this polytope, the vertices of the polytope are obtained by solving a linear system. And if you apply Cramer's rule on those linear systems, all of the points they're all rational points with determinants. Right? So essentially, all of these things are basically just determinants, like the coefficients. The coordinates of any of the points can be given as a ratio of determinants. And so just assuming, that you can then bound the size of the determinant, and then you can prove a bound of this form. And when you prove a bound on the volume, then you can apply the ellipsoid. And indeed, even proving this bound over here on this ellipsoid is not that difficult. I mean, it ends up being some algebra that I can explain quite quickly, which is simply what you do is you just consider the sphere, right, of unit radius sphere, and you just take this shaded region, and you argue that there exists an ellipsoid of volume, essentially a volume less than 1 minus 1 over 4n of the volume of the sphere that encloses the shaded region. So for the sphere, you can just do the calculation for the sphere, and then using linear transformations, it sort of works in general. Okay, so I've run out of time here. There are actually a few more things that I would like to say about the ellipsoid algorithm, and this is something that I will talk about maybe in the next lecture. But basically, I mean, the overall cartoon picture that you need to know about ellipsoid is given over here. This cartoon picture sort of captures the essence of the ellipsoid algorithm, and it's essentially some kind of binary search. Right? It's a fancy version of binary search over volumes, and the magic happens in the fact that the ellipsoid actually shrinks by a small amount, 1 minus 1 over n. But that's enough that if you do polynomially many iterations, you can shrink the volume of the ellipsoid exponentially. And once you shrink it exponentially, then using some sort of bound on the volume of a polytope, you can essentially prove. You get some termination criteria. Alright, so unfortunately I did go through the ellipsoid part fairly quickly. In the next lecture I might revisit. There are a few things I don't want to talk about, like the guts of the ellipsoid algorithm and get into the details, but there is this notion of a separating hyperplane which makes the ellipsoid really powerful. If you really think about this, you don't even need to have the LP. All you need is a separating hyperplane, and all of these things work. The ellipsoid algorithm works, and that's an important concept in optimization that I will talk about. But with that, I'll end, and I'll take any questions that you have.